Welcome. In this last video of this video series, we will be investigating a regression example. We will do so by using a very hands-on bike rental dataset. Now in this video, we will learn potential pitfalls when using linear regression and how to evaluate how good a regression actually is. We will do so by looking at errors, the root mean squared error, and the R-squared. We will also shortly consider various techniques on how to improve models. One of those is the concept of feature engineering. Let us first consider the business problem of this bike rental dataset. Now, we have a customer. The customer is called Capital Bike Share, and they are located in Washington, D.C. Now, the company rents out bicycles. Now, the challenge is to ensure that the right amount of bicycles at a given location for a given point in time can be ensured. Because clients, they want to rent bikes, and if there are no more bikes at that location, they cannot rent it. And so the company, they lose money because they miss out on clients, right? So the aim of the analysis is to predict the number of bikes for each hour of the day. This is very helpful so that the company, they can estimate at this day, this season, this month, how many bikes do they need to provide for potential customers. Now this of course only solves a small subset of the problem, because in this analysis we do not consider where those bikes are needed, nor how do we get those bikes to that location. So the whole logistics point of view is not considered in this prediction analysis. This problem is framed as a classical regression problem where we need to predict a certain amount of bikes for a given set of covariates. We will see in the covariate section so what our X variables are, that we have the season, the time, the temperature, the humidity, and the wind speed at that day. And now given those X variables, so given those predictors, we want to form an estimate on how many bikes are needed. Our task therefore is to build a model that predicts the bike demand given those X variables. Now let's get started with the first exercise. In this exercise, I will ask you to explore the data a bit on your own and try to find some first indicative patterns. Now, first of all, I ask of you to log into Azure, to create a new experiment, and then to drag and drop in the bike rental UCI dataset into the canvas and familiarize yourself with the data. In this case, we are again very fortunate since the bike rental UCI dataset is provided by Azure already on the platform. So we do not need to download any data. When looking at the data, the first natural question, of course, is to identify the Y variable, so the target variable, the variable which we want to predict. And of course, what kind of variables do we have in order to predict that variable? So what are our X variables? I think most of the X variables have a very intuitive name, but some of the X variables have quite some different categories which are not very intuitive. So they are maybe coded as 1, 2, 3, 4. And you do not know what 1, 2, 3, 4 is. So you need to check the variable description. You can do so by clicking on the link, and then you will get to a website where you will have a complete overview, what variables are included in datasets and how they are coded. So which numeric category has which meaning. This is very important in order to understand the data. Another related question is, do you see any leaking features? So that means, do you see any X variables which contain information about the Y variable? If we keep those variables inside our data, we will be able to perfectly forecast the Y variable because we have its information already included in our X variables. This is always something to look out for. Because of the time of forecasting, we of course do not have those variables at our disposal. As we already saw in the prior videos, it is of utmost importance that we identify which variables are of a categorical nature, because we need to tell Azure that these variables are indeed categorical, so they can be treated accordingly in our machine learning exercise. Some variables such as temperature, humidity, and wind speed have quite a particular scaling, as you will find out. Now, I ask of you that you consult the variable description in the link and try to figure out how they are actually scaled. Another question which you always need to question yourself is, which variables could be the most useful and which variables should I not include in my analysis at all? because they don't include any information which can be useful for our prediction exercise. Now, in order to check for some patterns, some first indicative patterns, I asked of you that you make a sample of 10% of the data and use the scatter plot feature like we learned in the prior videos. In order to be able to make a sample of 10% of the data, you can use the partition and sample module. Now we need to make this 10% sample of the data because in order to use the scatter plot feature of Microsoft Azure, the rows in our data are not allowed to exceed 2000. If there are more than 2000 rows, the scatter plot feature of Azure, it won't work. So this is one limitation of Azure. But by using the partition and sample module, we can somewhat bypass it and get like a first indication of potential patterns. This, of course, will not be accurate since it only reflects 10% of the data. So you should always try to validate it using the full data set, of course. Now let us start by logging into Microsoft Azure and creating a new experiment in the Experiments tab. Click on New and create a blank experiment. We now can go to Save Datasets, to Samples, and import the bike rental UCI dataset. We can also give our project a name, for instance, my bike rental dataset. Let us open the dataset. I think you all managed to do this by right-clicking and clicking on Visualize. So what we see is we have 17,000, a bit more than 17,000 entries with 17 columns. Now we have instant, date, day, season, year, month, hour, and a couple of different other variables. I think you all figured out that the Y variable of interest is the count variable. So the count is just on a particular day, how many bikes were rented given these X variables. And we have more information, not only the day, we also have the hour on how many bikes were rented on that particular day and at that hour, and in which month, and whether or not there was a holiday, what day of week it was, whether or not there was a working day. And we also have the year. So if we check the year variable, we have two entries, min 0, max 1. So we have 50% of the data is 0 or 1. This means that we have observations from 2 years. This is quite convenient because we can use this as a natural training and testing data sample, where we first train our model in the first year, so year 0, and test the model then in the year after that, so in year equals to 1. So to sum it up, the Y variable is our count variable, and all the other variables here are potential X variables. However, we have two additional variables, casual and registered. So casual users are users that rent bikes very casually and are probably not registered with the bike rental company. And registered users are users which use the bikes much more often, probably have some kind of registration which permits them to rent the bike much quicker. If you pay close attention, you will see that 3 plus 13 equals 16. So the count variable is simply the sum of the casual and the registered bike rentals. If we leave these two variables, casual and registered, in our data and try to predict count, we will have a perfect fit because we can explain count perfectly by the sum of the casual and registered variables. We of course do not have these variables real time when we want to make a prediction, because only afterwards, when the count already has occurred for that particular day at that time, we also can observe the casual and registered variables. So in order to conduct the correct analysis, we need to omit these variables. The next question is, which variables are categorical? Because we need to tell Azure that these variables are categorical in order to perform the analysis. Now this is always the first step. In an analysis you always need to go variable by variable and you need to check them. So in our case, the season, we have 4 different indicators here. So 1 through 4, the year, which goes 0 to 1. But we will not code this as a categorical variable because we only need to use it as a splitting criterion for our training and testing samples. Another categorical variable is the month, 1 through 12, and the hour, so from 0 to 23. We also have holiday is also a categorical variable, as well as the weekday. Working day is also a categorical variable, as well as the weather situation. Now, the weather situation is 1 to 4. You probably don't know what that is, right? So you need to check the variable description from the link. If we quickly follow the link, we see that the weather situation is coded from 1 through 4, with 1 being the best weather and 4 being really bad weather with heavy rain, ice spells, and thunderstorm. Now, if we go back to the data, we see that these 4 variables, temperature, temp, humidity, wind speeds, are coded quite weirdly because they have a very weird scale. Normally, temperature is indicated in Celsius or Fahrenheit, and certainly not 0.24. So what we see is that we have a minimum from 0.02 until 1. temp is very similar. Humidity is also from 0 to 1. And the wind speed is from 0 to 0.85. Now, if we want to know why the scaling is this particular, we need to again consult the variable description. Now, if we again consult the variable description, we see the temperature and temp, so the feeling temperature, how hot or cold it actually feels for the person, are normalized via this formula here. So this just presses the scale, which ranges from -8 degrees Celsius to 39 degrees Celsius between 0 and 1. The same is done for the temp variable, and the humidity variable is also just divided by 100, which is its maximum. The wind speed variable is also just divided by its maximum of 67 probably miles per hour, because kilometers per hour would be a bit low. Now, why are these transformations done? It is not mandatory, but a couple of algorithms, they find it more easy to learn from the data if they have some kind of standardized scale and are not very heavily affected by these huge variations. But in principle, it shouldn't matter for a lot of algorithms. Let's get back to the data. I think we can all agree that temperature information, what kind of day it is, which month it is, the hour, of course, and which season it is are very relevant variables. But here in the beginning we have 2 variables, so the instant and date day. The instant is simply just the row number and it will not provide us with any insight when we make a prediction. Similar is just the date day. If you look at this variable, we see 2011, 01, 01, and the time is here always the same. So both of these variables, they have absolutely no prediction power when we want to analyze this data set in order to be able to predict the number of bike rentals for a given hour on a given day. So for the following analysis, we should simply just omit these variables. Now let's continue our analysis by just investigating whether or not we can identify some basic patterns in the data. We can do so by using the partition and sample module and taking a 10% sample of the data in order to use the scatter plot function. We type in partition and sample, drag and drop it to the screen, and connect its input node with the data set. Now here we can do the rate of sampling, so 10%, and click run. This will now give us a 10% data sample of our full data set. Now we see we are well below the 2000 rows, which is the maximum in order to use the scatterplot function. Now we want to analyze if we can see some first patterns. which relate to the count variable, so the number of bikes rented. Now we see the histogram of the bike rentals, so how they distributed. Now we want to compare it to see some patterns to other variables of interest. We can do so, for instance, with the temperature. What we see here is that when the temperature rises, so when the temperature is higher, there are more bike rentals on average. So there is an upward trend in bike rentals when the temperature is better. So this could also indicate that if the weather is good, people like to ride bikes more. Another variable of interest could be the humidity, as humidity is not so comforting if you ride a bicycle and you sweat a lot. What we can see here is if the humidity is really high, bike rentals, they tend to be a bit lower. And when humidity is lower, they tend to be a bit higher. So these are some first patterns that we can just see from the data. Another variable which should be obvious is the wind speed. You don't like to ride bicycles when it's really windy, right? So what we see is a bit of a downward trend. So if the wind speed is a bit lower, there tend to be some more bike rentals. But all these patterns are not that very clear, but we see some first indication in the data. And we also have to keep in mind that we only use 10% of the data in order to make these plots. Now in this exercise, I want that you train a first model, and this first model we will train a linear regression. Now the purpose of this exercise is that you are able to train this linear regression and that you then open the score model module and you investigate the scored labels column. And the question is, what do you observe in that column? As we know, the scored labels, that is simply the prediction of how many bikes are going to be rented from our model. In order to do this exercise, you have 5 important steps. So the first step is to identify your factor variables, so the categorical variables we just discussed. And we need to tell Azure that these variables are indeed categorical. In the third step, we need to delete the 2 irrelevant variables and the 2 leaking features. In order to perform the machine learning steps, we need to build a training and testing data. As we already discussed, we have a natural split criterion, which is the year. So we have observations from 2 years. From the first year, we train the model on it, and we test the model on the year it did not see, so the future year. We can do so by the split data module. We set the splitting mode to relative expression and then specify the relational expression you see on the slides. You then just train a linear regression like all the other classifiers we did before, and then you inspect the score model module. So let's get started by telling Azure which variables are categorical. We do this with the edit metadata module. Launch the column selector. And here we have the season. The year we will only use for splitting, so we will not define it as a categorical variable here. The month, hour, holiday, weekday, working day, weather situation. These here are numeric. Now let's drop the 2 irrelevant features and the 2 leaking features. We can do this with the select columns in dataset module. Now first in the edit metadata module, we still have to change the data type to string and make them categorical. Data type we wouldn't necessarily would have to change the string, but it also doesn't hurt. Just to make categorical is really important that you select this option here. Now with the select columns in dataset module, we can exclude the 2 irrelevant features and the 2 leaking features. We can do so by starting with all columns and excluding those 2 irrelevant features, instant and date day, and the 2 leaking features, casual and registered. Now it's always a good idea to visualize whether or not your changes were actually reflected in the dataset. We can do so by simply running the whole project. We can now click here Visualize, and what we see is the two first columns, they were now excluded, and that now also the two last features, the register and casual, they were also excluded, those two leaking features. We can also see that hour is a categorical feature, as well as month, holiday, weekday. Weather situation is also a categorical feature. So all our changes were actually now reflected in the dataset and updated. Now let us split the data into training and testing data. Do so with the split data module. Now in prior videos we always did the split rows option, so it just selects randomly rows according to a fraction. In this video, however, we already discussed about the year variable, where we have 1 year which we use to train the model, and in the future year, which we did not see before, we will test the model, how good it actually is. We will use the relative expression option. Column name is YR, and this should be equal, so two equal signs to 0. So this will give us, in the left node, that will give us the training data year equal to 0, and in the right hand node, it will give us the testing data with year equal to 1. The next step is simply to train a linear regression. Do so by using again the train model module. We have the linear regression. Then we also need the score model module. Then we also need evaluate model. So these steps are always the same. Now we just need to connect the nodes into the right place, like we did before in all the prior videos. And in the train model module, we also need to tell Azure which variable is actually our Y variable. This, of course, in our case, is simply the count. So this is all set up, and now we can run the experiment. Now let us simply recap what the objective of this exercise actually was. It was to train a linear regression. We did this. But now we need to look at the model's predictions. So in the score model module, what are the scored labels? Scored labels are simply the predicted number of bikes given a particular day, given the hour of the day, given the temperature, the humidity, the wind speed, and all the other covariates, so X variables that we have. And the question now is there something special about the model's predictions? We can investigate what the predictions on the testing data our linear regression gave us by clicking on the score model module, right-clicking and clicking on Visualize, and investigating the scored labels column. So the scored labels are simply, this is the predicted number of bikes that the model told us were going to be rented out, given all our X variables on the new data, so the testing data set. Now what we see here, which should be obvious to you, we have a predicted negative amount of bikes rented. So -10, -29. The actual number was 75, but the model predicted there was going to be -44. Or here we have an actual number which was recorded afterwards was 52. But the model predicted us that beforehand, for that particular day and that hour, there would be a total number of bikes rented of -60. This absolutely makes no sense, right? How can you rent out a negative amount of bikes? We can also just go into the scored labels column and check the histogram. This also shows us that we have quite a couple of predictions which were negative. Now, we might ask ourselves, why is this the case? What is wrong with the linear regression? So if you recall how the linear regression is actually set up, we just estimate some coefficients, then there is a additive structure. So additive structure, this means that the features, they are multiplied by a coefficient and all added up. Now this can result in there being negative predictions. That is one of the limitations of the linear model. So instead of just never using a linear model, we should just realize when it is sensible to use a linear model. And in our case, we only have positive numbers, so count numbers, which cannot be negative. So it's really not sensible to use a linear regression in this setup, because linear regression can result in negative predictions. A variant of the linear regression, so where we restrict that we only have positive outcomes, so positive predictions, is the Poisson regression, because it simply fits it to a Poisson distribution, which is suited for count data. Another option, of course, is just to use decision forests or boosted trees. They will also not result in a negative prediction. So this is just something to keep in mind and really important. Now, a very interesting question you should always look at when estimating models is to investigate whether you have a tendency to over or underestimate the y variable. You can do so by simply generating errors. So in this case, I just define the errors as your model predicted y, so your prediction, minus the actual effective bike demand on that day. Writing the errors in this way results into having a nice interpretation. So if this difference is negative, this means that you have an underestimation. So for instance, if you predicted that you had 20 bikes, but there were actually 30 rented out, you predicted that you had 10 bikes too few. So you underestimated the actual bike demand by 10 bikes. This is quite a nice property to have and makes things much easier. A lot of the times you will see that errors are defined by subtracting the model predicted y from the actual y, so the other way around. But then you don't have this nice interpretation with the sign. Now, as a first step, simply connect the apply math operator module to the score model module. In a second step, just click on the module and change the properties like you see on the slide. After that, you make a histogram of the error column in the results dataset of the apply math operation module, and you will see very quickly whether or not you have a tendency to over or underestimate the bike rental demand. Now let us quickly do this in Azure. We search the apply math operation module, drag and drop it here, and connect it to the score model. We then adjust the options, the properties of this module, as in the slides. We have to go by name. Deselect these, that we only have count. And this column selector, we include only the scored labels. Now we can run the experiment. We can now view the results by clicking on the Apply Math Operation module and visualizing it. Now in this column, we have the residuals, so the errors that we made. So the model predicted y minus the actual y. We recall that a negative number means that we underestimated actual bike demand, so that our model's predictions were too low. We can make a histogram, and what we see is a lot of predictions. So definitely all these underestimated actual bike demand. So our linear regression does indeed have a really big tendency to underestimate actual bike demand. This is not a good property to have in a model, and you should definitely try to adjust. Now, how can you adjust? Now, generally speaking, you would always try to find new variables, create new variables from existing ones. We will talk about that later. But in our case, most importantly, we just saw that the linear regression is not appropriate, so we would have to change the model. Now this ties into our next topic, one of the most important topics of this video, namely, how do we actually measure model success? Now, just generally speaking, the model is better if the regression line can follow our data points more closely. Now, this means intuitively smaller errors, so the ones we just calculated, suggest that the regression line can better follow our data points because we don't under or estimate that much. Now, if you want to do this in a formal way, so with mathematics, you would just say that the smaller root mean squared error suggests a better model. Now, this sounds like a really fancy term, root mean squared error, but it's actually quite simple if you work backwards. So we have the error, the E, right? Then we have an S, which stands for the squaring. So the squaring of the error, it removes the sign, so the over or underestimation. And in addition, it increases the importance of really big errors. So a really big error will get squared and is even bigger than the M. It stands for the average of the squared errors. So you take the average of all the squared errors in your sample. And then at the end, we still have the R. The R is simply the root, and we take it to get back to the original scale because we don't want to look at errors in squares. So a smaller root mean squared error generally suggests a better model. It's all back to the intuition of smaller residuals, with the twist that really high errors are really weighted a bit more. An alternative is just the mean absolute error. There you don't take squares. And that metric has a bit of a better interpretation, but is not commonly used because the root mean squared error has better statistical properties. Now finally, what is always looked at is the R square of a model. And the R square simply states what percentage of the average fluctuation around the Y variable can be explained by the model. A nice feature of the R square is that it typically ranges from 0, which is a total useless model which cannot explain any fluctuation around the average Y variable, to 1, which indicates it's a really, really good model and it's the maximum we can do. The actual size of the R square naturally always depends on your application. For some contexts, it's really, really hard to get a high R square. So it's best to always just compare R squares maybe to your prior approach. Like in the past, you already have a model in your company, and that model's R square is much lower than the one you have now. So this suggests that your new updated model can predict the target variable much better. Now, Azure very conveniently already calculates all these performance metrics for us. We can simply click on Evaluate Model, visualize it, and here we have the mean absolute error, 110, the root mean squared error, and the coefficient of determination, which is simply the R squared. What we also have is the error histogram here. But just bear in mind, this is in absolute terms, so it's not useful to look at a tendency to over or underestimate. Now in our example, a mean absolute error of 110 implies that on average, we over or under predict the count variable, so our target variable, by 110 bytes. If we recall the distribution of the count variable, so I think the maximum was like 800 or 900 bytes. I think this is quite a large number. Now with using a linear model, the coefficient of determination tells us that we can explain roughly 43% of the fluctuation around the average value of the target variable. In our next exercise, so exercise 8, we want to compare different model predictions. We already established that the linear model is not appropriate, and I already gave you a couple of suggestions of alternative models I would use in this case. So up next, you should train on yourself 2 machine learning regression models predicting bike demand. I ask of you to compare the performance of the 2 models and just paying particular focus on the metrics that we just discussed. So these include the residuals, the root mean squared error, and the R squared, and you can also look at the mean absolute error. Residuals just means errors, so it's just a fancy word for the same thing. but it's very commonly used in machine learning context, so you should know. Now, as a further additional question, just while you're doing the exercise, you can maybe think on how you could improve the performance of your model. I already hinted it in the prior discussion on how a model could potentially be improved. So let's get started by comparing two different machine learning algorithms. Keep in mind that you can simply use the very easy feature of Azure and simply copy modules, so you don't have to again drag and drop them into the canvas. Now in this comparison, I will use a Poisson regression and a boosted decision tree regression. We can start by simply copying the modules, which we effectively also need for the other analysis. This is the train model module and the score model module. We also need the evaluate model, but we will copy it later on because we only need it once. Now we need to copy the second time because we have two different models. And the evaluate model we only need once because we have two input nodes. Now we can drag and drop in the Poisson regression and the boosted tree. Now we only need to connect the nodes and we are done. So we have the training data. Then we have the testing data, which we use in the score model module. Then we need to input the predictions into the evaluate model module in order to do the comparison. Now we also need to connect the models to the train model module. And here we still didn't connect the training dataset yet to the train model. So I think this is it. Now we can simply run the model. We can view the results in the evaluate model module by visualizing them. What we see here now is the Poisson regression on the left-hand side and the boosted tree regression. We see it on here on the right-hand side. Now, if we compare with before, we had now squared in the linear regression of around 43%. So the Poisson regression is not that much better. So we have 45 versus 43. What we see, however, the boosted decision tree regression is much better. It has an R-squared of 63. The mean absolute error is also roughly 91 in comparison to 110 with the linear regression. So the boosted tree regression is much better. Now if you apply the same procedure as before and simply copy the apply mass operation module and view the histograms of the errors, you will still find that there is a significant degree of underestimation of the actual bikes rented. Going from a linear regression to Poisson regression, it hasn't done much in terms of underestimating the actual bike rentals. With the boosted decision tree regression, however, we were able to curb this underestimation a bit, but we still have a high degree of underestimation. Now, as I already pointed out, there are several ways on how we can improve model predictions. One of them being that we simply look at our data and we construct new features from already existing ones in order to give the model a bit more leeway in what it can look at and what patterns it can discover. This process is called feature engineering, and if one wants to improve one's model, one has to do it. It's very important. Now, as I already mentioned a couple of times, by creating additional variables from already existing ones, we can typically further improve the performance of most machine learning models. This works because we give the algorithm a further hint on potential patterns, or simply by simplifying patterns, the algorithm can more easily recognize them. Now, important feature engineering tricks includes considering temporal dynamics. That means that we include prior variable values as new predictors. For our bike rental data, this could mean that we want to consider that if there's a trend in really high numbers in bike rentals, for instance, an hour ago or 2 hours ago, this could mean that the next value, so the one we want to predict, is also going to be higher. We can consider this by including these values. What is also a very useful trick is to categorize numeric variables. We already saw these histograms. That already is the first categorization. Sometimes it doesn't make sense that you have very, very high values in a variable and there are only a few. So it might make sense just to include a category which indicates all values above a higher threshold. Because what happens in a lot of algorithms that these outliers or very extreme values, that they really significantly reduce the performance of the algorithm. What is also a good technique is to summarize categories. So if you have many categories, and let's say 90% of the observations are in 4 categories, and then you have another 10 categories with very, very few values, it might make sense to summarize those categories with very sparse observations into a new category, maybe called other. Another technique, which is a bit more advanced, includes creating interaction terms. So that just means that we, for instance, multiply 2 variables and include that as a new feature. One typically does this if one suspects a pattern to be different for a particular value of a variable. One example would be, for instance, good weather and a holiday, that those occur at the same time and that the effect is considerably different. So that there are many more bike rentals when there's good weather, and additionally if there's a holiday occurring at the same time. We can simply consider this pattern by including temp times holiday as a new feature. Now in this last exercise 9, we want to investigate the added benefit of conducting feature engineering. To do this, we already prepared for you 2 datasets. In one of the datasets, bike rentals 2.csv, we added past bike rentals up to 12 hours ago. This means that you will have new X variables, which indicate in the past hour how many bikes were rented, or 2 hours ago how many bikes were rented then. By including these new features, we should have some benefits from these temporal dynamics. So if there's a trending behavior in bike rentals, so when bike rentals were really high a couple of hours ago, they probably should also be higher in the future. In the second dataset, we also provided for you bike rentals 3.csv. In addition to adding the bike rentals up to 12 hours ago, we also added bike rentals up to 12 days ago. That means for a given observation, you will have the bike rentals, for instance, yesterday for the same time. This even gives you more flexibility with regards to temporal dynamics. So you should do a model comparison, but instead of varying the type of algorithm you use to predict the number of bikes rented, you should vary the input data. One of the input data is the bike rentals 2.csv dataset, and the other input data for the second comparison is the bike rentals 3.csv data. Doing this double analysis, so doing this comparison of input data, you can effectively analyze if feature engineering is actually worth it. Now, because we did this model comparison stuff already a couple of times, I really trust that you can do it now on your own. And instead of showing you the whole procedure again in Azure, I'm just showing you some summary results. So as my algorithm, I chose the boosted decision tree regression, and the 2 charts on the right, those are the ones which include the feature engineering. So the chart in the middle, it includes the feature engineering with the additional features of up to 12 hours ago bike rental. Whereas on the right-hand side, we also have the feature engineering that includes past bike rentals up to 12 hours ago and also up to 12 days ago. Now, what we see in comparison to the first chart, which doesn't include feature engineering, is that we were significantly able to reduce the degree of underestimation. Now the bars are much more centered around 0. This is at the end just what we want. We don't want to systematically under or overestimate our bike rental demand. Going from the bike rentals 2 CSV file to the bike rentals 3 CSV file, we see that the performance metrics do not get much better. So a root mean squared error from 90 to 81, and the R-squared only from 81 up to 85. But what we can see is that the errors, they get more centered around 0, and that is a positive thing. But always keep in mind, the more features you add, you increase model complexity more, because the model has much more information to choose from. This makes it even more important that you only evaluate a model on testing dataset which the model did not see before in order to avoid overfitting. Now, to sum it up, we were able to predict the number of bike rentals quite good. Just keep in mind that there are also other aspects to this analysis. For example, we threw away the casual and the registered users, right? In the beginning, we threw those variables away. Now, what you could do alternatively, which would actually be quite smart from my point of view, that you model the casual and the registered users separately. And at the end, you simply add up the predictions in order to get the total count variable of bikes rented. Doing this, you could even more take into account the differences between casual and registered users. For example, registered users, they might much more likely to also ride a bicycle in the rain because they just use the bicycle to go to work every day. Whereas on the other hand, casual users, they probably only go on good weather or when they have a holiday or have some free time in order to enjoy some cycling. Now, to sum up this rather long video, let's just make a couple of remarks which you really need to pay attention to when conducting regression analysis. If you have positive count data to predict, you really need to watch out with the linear regression because you can get negative predictions, which you absolutely do not want and do not make any sense. Furthermore, when evaluating a couple of different models, which you should always do, smaller residuals that are centered around 0 are generally preferable. You do not want to have systematic under or overestimation of your target variable. Finally, you can substantially improve your model prediction by doing some clever feature engineering with the techniques we discussed. Most important being the temporal dynamics, the categorization of numeric variables, and summarizing big categoric variables which only have a few data points inside them. Thank you for watching.